Geography, topic 1A, which is the challenges of natural hazards. So how this is going to go is we're going to go through the content according to the spec, which you can see in the middle of the screen. And as we go through the content, we'll make sure we cover everything, we revise everything, and then after that, we're going to do some exam practice questions that should help you remember and reinforce the information we just learned. So let's go through the topics now. So here you can see the specification. So each of the specification for geography is really helpful actually because there's different bullet points, and for these different bullet points you can then test yourself on it. So you can test yourself using the specification. So the first point of the specification is you need to define what is a natural hazard. So a natural hazard is a natural process which can cause death, injury, or disruption. So what you need to be thinking about when you think of natural hazards is death, injury, or disruption. Now, a natural hazard is actually different from a natural disaster. So a natural disaster is when you're talking about it in past tense, and it's something that's actually happened. So if we're defining a natural hazard, that causes death, harm, or disruption. Now the next point is types of natural hazards. So in terms of types of natural hazards, we have geological hazards and meteorological hazards. Now, geological is all to do with plate tectonics, whereas meteorological is all to do with weather systems. So examples of geological include volcanic eruptions, and geological hazards include things like volcanoes, earthquakes, landslides, avalanches, and meteorological events include things like tropical storms, flooding, drought, all of those. Now we then asked what factors affect the hazard risk. So we need to see factors affecting the hazard risk, which is basically what factors increase the chance of you being affected by hazard. So hazard risk is the chance, let's represent that by percentage, the chance that you will be affected by a hazard. Now, things that increase the hazard risk include things such as the population. The more people there are, the greater the hazard risk. The landscape as well. So is it a floodplain landscape where it's just flat, or is it hilly, a mountainous area? Because that will affect how badly they're affected. Also the time of day, the date that it happens, the capacity that a population have to cope. You could also say the economic status of a country. And finally, some things just about the natural hazard itself. So the type of natural hazard, the magnitude of the natural hazard, which is how strong it is and how great it is, and the frequency of natural hazards. How often does it affect that area? Therefore, are they more prepared and are they expecting it and used to it? Now, the next thing that the specification requires you to know is on the next page, and it's earthquakes and volcanic eruptions are the result of a physical process. So explain plate tectonics theory. It's important to remember that plate tectonics and everything you learn about it are just theories, of course, because there's no confirmation of this. So plate tectonic theories. So the first theory and the main idea is that the Earth's crust. Well, let's start by looking at the structure of the Earth. So we believe that the Earth has this structure: inner core, outer core, mantle, and crust. And we believe that the crust here is made up of jagged pieces of rock, and these jagged pieces of rock we call tectonic plates. Now, not only this, but these tectonic plates are moving. They're constantly moving. Why are they moving? Well, the theory mainly suggests that they move because of convection currents in the level below, which we call the mantle. And because of these convection currents, which are transferring heat up and down, they cause the movements. Now, there's actually two different types of crust that you're going to need to know. The first one is what we call oceanic, and the second is continental. So the oceanic sits on water, and the continental sits under the land that we sit on today. So oceanic is actually, and continental have different properties. So continental is actually much thicker, however, it's less dense. Dense is how many particles are compact in an area. So it's going to be thicker, but the particles will look, for example, like this, whereas oceanic is thinner but more dense. So oceanic could look like this, but the particles are much more close together, like this. Now, the densities are really important in plate tectonics theory, and we'll look at that now. One more thing, another key word that you need to know is plate margins. Now, these are often called plate boundaries as well, and what they mean is just where the plates meet. Okay, these are also really important. So there are three types of these plate margins now. We believe. So the first one is destructive, where the plates pull apart from each other. The second is constructive, where the plates collide with each other and then both move upwards. And then the final one is conservative, where the plates slide past each other in different directions or at different speeds. Okay, so let's dive more into it. So in terms of destructive, two plates move towards each other. So there's different scenarios. So if it's oceanic and continental, the less dense plate will be subducted beneath the more dense plate. No, sorry, the denser plate is subducted. So what we mean by that is we have two plates moving towards each other. And what happens is the denser oceanic plate then subducts into the mantle. And the continental just keeps pushing forward like that. So this oceanic plate dips into the mantle. This is what we call subduction. And we're saying that if there was an oceanic and continental, the oceanic would be subducted because it's more dense. But what if we had continental and continental? This means that they are roughly the same thickness. Now, when they're roughly the same thickness, what happens is none of them want to subduct, so they actually both move up like this. And then they then create ripples like in the land surface, which is what we call mountains. They fold. So that's why mountains are often created on destructive plate boundaries. We call these fold mountains. Now, constructive is when there are two plates moving away from each other. And because they are moving away from each other, sorry, I got the arrows messed up. And because they are moving away from each other, they construct a volcano in the middle of it. So no matter what plate it is, as they both move apart, they then cause magma to rise in the center. And then the magma then rises and creates a shield volcano. So the two plates move away from each other, the magma rises to fill the gap in the crust and cools, creating new crust and shield volcanoes. And finally, conservative, when they're moving past each other at different speeds or different rates. Now, what happens here is as they're moving past each other, friction can often build as they can get stuck because they're not perfectly straight lines, as you can imagine. And as this friction builds, this then means that when it's released, this release of friction that happens after it releases so much energy that it releases it in waves, which we call seismic waves. And this whole thing is what we call an earthquake. And this process is entirely random and you can't predict it. So volcanoes can occur at constructive and destructive plate margins. So you're often going to be asked in the exam, why would they occur and how does it occur? So let's go back to the plate margins and let's look at how each thing occurs. So we have destructive, which is oceanic and continental. Now, how can we say volcanoes form? Well, what happens is we know that the denser oceanic plate gets subducted. And then after this happens, it then melts in the magma due to the heat and forms a pool of magma. And then what happens is this pool of magma then rises through the cracks called vents. So it rises through cracks in the crust. And as it rises back up, it then can erupt the vent, creating a volcano. So that's how destructive volcanoes form. Now, how do they form at constructive? So constructive, as we said, what happens is as the two plates pull apart, the magma then rises in between the gap and it then forms a volcano. However, some volcanoes form and they're not actually at destructive, constructive, or conservative. And this is what we call hotspots. Now, this is just areas over the mantle which are really hot. But not exactly plate tectonics either. Because it's not at a boundary, it's just an area that's really hot. And because it's so hot, it creates volcanoes despite there being no plate boundaries. So that's what's special about hotspots. And a key example of this is the Hawaiian Islands. Now, earthquakes, however, can occur at all three plate margins. And let's see how. So in terms of destructive, earthquakes happen as the two plates collide against each other, friction and tension builds. And as the denser plate is being subducted, then there's also a lot of friction here, and this friction is then released as energy. Now, constructive, as the plates move away from each other, they then cause friction into the parts where they're moving away from each other. So the friction builds in the cracks, which is called earthquakes. And conservative, as plates slide towards each other, they get stuck in one another as they grind past each other. And then they get stuck. Now, these three all get stuck, and then what happens is they then jerk, and all the energy is then released through massive shock waves, which we said are seismic waves. Now, just some key information about earthquakes. If we were to look at a diagram, so imagine this is the land, and this is the mantle. And now what's happening here is this point is what we call the focus. The focus is where the mantle directly starts the earthquake. So the point in the earth where the earthquake starts. The focus where the earthquake begins in the mantle. So focus, point in the earth where the earthquake begins. Then we have the epicenter here. Now the epicenter is the point at a 90-degree angle directly above the focus that shows where the earthquake first targets the earth the strongest. So the point on the earth's surface directly above the focus. Now, the epicenter is where the earthquake is felt the most. And then we have these seismic waves, which look like this. which are then released. And they get further and further apart as it gets weaker and weaker the further you go from it. Now, the moment magnitude scale is the amount of energy released by an earthquake. So we call this the magnitude. The amount of energy released by the earthquake. So magnitude is the amount of energy released by the earthquake, and it's measured using the moment magnitude scale. Oh, just as to your request, go over global atmospheric circulation. Okay, I'll do that now. Thank you for your request. Sorry, I did not see that until just now. So let me go over global atmospheric circulation. I know that can definitely be a tricky topic. So thank you for your request. So, okay. So global atmospheric circulation, so let's just abbreviate it to GAC, or the transfer of heat from the equator to the poles. So imagine here we have the Earth, and this is the center. The center is what we call the equator, and this is where the sun heats the most strongly. So at the equator is the hottest part of the Earth. Now, what that means is, as the equator is the hottest part of the Earth, we also have the poles, the North Pole and the South Pole. Now, the poles are the coolest parts of the Earth because they're furthest away from the sun. Okay. So what you now have here is we have a cold part of the Earth here, and then we have a hot part of the Earth here, and then we have another cold part of the Earth here. Now, what global atmospheric circulation is the transfer of heat. Because heat doesn't just stay where it is, heat moves across. And because there is a difference in temperature, heat then moves from the equator up to the poles, and then the cool air just comes back, and it's a cycle. And then the hot air goes from the equator to the poles, and then the cool air brings it back to the equator. So that's how it cycles around. Now, why does the air move? Specifically, air moves because of differences in pressure. Okay. So air moves because of differences in pressure. So what does this mean? Air moves from areas of high pressure to areas of low pressure. Now, let me just explain one more thing, 1 second. Let me double check something. Okay, so in terms of what high pressure and low pressure mean, high pressure is cold air. So because cold air is dense, what happens is high pressure is when cold air is, because it's dense, it then has high wind speeds and precipitation and rain and things like that. Whereas low pressure is when there's warm air. And because there's warm air, this means that it's less dense. So the warm air then rises. And because it rises, that means that there's very low wind, it's very humid, and it's very dry. So those are the conditions. So that's why air moves, because of difference in pressure. So it moves from areas of cold air and dense air to areas of less dense air. So what it's basically saying is it moves up. Air moves up. Because high pressure is close to the surface of the earth and low pressure is close to the atmosphere, so higher up. So air moves up. That's all you need to know from that. Now, the global atmospheric circulation system is divided into different loops. So let's look at the loops now. If you don't understand anything, feel free to tell me because I can re-explain it. Okay. So imagine that's Earth. And we've got the equator here. So here, degrees. This is 30 degrees north of the equator. This is 60 degrees north of the equator. This is 30 degrees south of the equator, and this is 60 degrees south of the equator. So you don't need to know these for the exam, just roughly so you can tell where the equator is and where the different parts are. So now we know that the sun warms the earth part, as we discussed. Now, because it is the hottest part, and we know from this that when we have warm air, it rises. So at the hottest part, we know that warm air rises. Okay. As the air rises, it cools. So as the air goes up, the higher the air goes up, the cooler it gets. And then what happens is it then moves from the equator. So as the warm air rises, it then gets cooler and moves upwards or downwards. So as air rises, it gets cooler and moves away from the equator. Okay. So the warm air is hottest at the equator. It then rises and moves towards the North Pole and towards the South Pole. Now, approximately 30 degrees north and 30 degrees south of the equator, the cool air, that cooler air is, and therefore it sinks and creates high pressure. So the warm air rises here, and at 30 degrees north, the cool air sinks. And here as well. Now, this then creates something called a high pressure belt. This is just some terminology that would be helpful. So this is called a high pressure belt. And that as well. Now, as the ground surfaces, the cool air then either moves back to the equator or towards the poles. Now, the air that moves back to the equator is what we call trade winds. So this is the air that returns to the equator. But some air doesn't return to the equator. Some air then keeps moving up, and this is called westerlies. So westerlies are the air that keeps moving towards the poles. So you may, whenever you hear the weather, know when they're talking about westerlies or trade winds, this is what they're talking about. So when they're talking about trade winds, it's the air that has sunk and is moving towards the equator, and if it's westerlies, it's the air that's moving away from the equator. I hope I'm not confusing you because there's a lot of writing here. So, the reason why these winds don't go straight up, they curve, is because of the curvature of the Earth. So the Earth obviously curves like this, and because of that, this causes the winds to curve. So winds curve due to the curvature of the Earth. Now the reason I'm saying this is because of the curvature of the Earth, as well as Earth rotating constantly. So two reasons that winds curve. Firstly, due to the curvature of the Earth, and then secondly, due to the whole effect, the Coriolis effect. So the Coriolis effect describes how winds curve due to the curvature of the Earth as well as the atmosphere and the Earth's rotations. Now, so that means that the Coriolis effect then causes the westerlies, or the trade winds, to move in a curved way and therefore spread out. Now let's look at what happens 60 degrees north and 60 degrees south of the equator. So at 60 degrees north and south of the equator, what happens here is that the warm surface winds meet with the cold air from the poles. Because imagine this is a cold area, the North Pole. So the cold air is then meeting with the westerlies, so the warmer air, the westerlies, because the westerlies have just been warmed by the equator, whereas the North Pole air is cold. And what happens is then the warm air rises. So the warm air rises, and when we see warm air rising, it then creates low pressure. So at 60 degrees north, it's an area of low pressure. Now the same thing as 60 degrees south. So the South Pole air is then meeting with the warmer air from here. So with the warm air from 30 degrees south, and when they meet, the warm air rises because there's more warm air, creating low pressure. Now, that means that we have different things that happen at each part. So we have something that happens at the equator, something that happens at 30 degrees north and 30 degrees south, something different that happens at 60 degrees north and 60 degrees south, and yeah, so there's three different things occurring. And they then summarize these three different things through three different cells or loops. So let me draw on the loops now. Okay, I'll draw in black. So the first loop is, as you can see, it starts from the equator and we have Hadley cells. So let me do it on this side of Earth. So you've got So imagine this line is the equator. That's the equator. So the first cells we have are called the Hadley cells. We know that at the equator there is low pressure because it's very hot and the warm air is rising, so there's low pressure here. So we have two cells above and below the equator, which is called Hadley cells, and this continues up until 30 degrees north and 30 degrees south of the equator. Then we have another cell, and this cell is called the Ferrel cell. And then finally, after Ferrel cell then stops at 60 degrees north and 60 degrees south, and we have the final cell, which is the easiest one to remember, probably the polar cell. Now my diagram is not really good because the circles look kind of irregular by the cells, is that at the Hadley cell, for example, what we're going to see is we're going to see the warm air from the equator rising. So this is the warm air rising. But then remember we said that at 30 degrees north and 30 degrees south, the cool air then sinks. So then we see here, the cool air sinking. And here. But then we see the Ferrel cell, and the Ferrel cell begins at 30 degrees north, and we said that the air that keeps moving is called the westerlies. So then what happens is the westerlies then heat up again. The westerlies heat up, but then it then sinks as it gets colder towards the poles. But then remember we said that when it interacts with the North Pole's cold air, this warm air then rises. And the cold air from the polar cells then sinks. So those are the different cells. We've got Hadley, Ferrel, and polar cells. And that is global atmospheric pressure. You could also talk about how global atmospheric pressure affects weather around the world. So overall, if you're asked to describe what global atmospheric circulation is, you'll just say how air transfers heat from the equator to the poles. Okay. How air transfers heat to the poles. Now you may be asked, how does it influence weather or climate? So some things you could say is that at the equator, the sun is directly overhead. So at the equator, because the sun is directly overhead, this means that over there the Earth receives lots of solar radiation. And therefore it's hot. So it's hot weather. And also lots of low pressure. And also because the hot air then rises, and we know that warm air rises, this then creates lots of precipitation and rain. And what do we know is at the equator that has lots of precipitation and rain but also is very hot? Well, that's the Amazon rainforest. So the Amazon rainforest largely exists around the equator, And we know that there's lots of solar radiation, which explains loads of plants, but there's also lots of precipitation and rain, which also explains how there's loads of plants being able to grow there. Now, we know that 30 degrees north and south of the equator, we saw that it's where the cool air sinks and it's high pressure. Oh no, sorry, I was reading the wrong one. 30 degrees north and south is when there's quite dry conditions. Because remember, the heat is hottest at the equator, and then slowly it gradually gets cooler and cooler, but it's still relatively close to the equator, so there's little precipitation and quite dry conditions, and that's why we get deserts. One second. That's why we get deserts at this latitude. And then finally, we have where the UK is. So the UK lies close to the low pressure zone of 60 degrees north. So the UK is roughly somewhere along here because it's 60 degrees north. Now, what do we know about 60 degrees north? This is where the warm air from the equator interacts with the cold air from the North Pole, and the warm air then rises, but then there's also lots of wind. And so overall, it's a relatively low pressure zone. But then we also have the westerlies, which we were talking about, which makes it a very windy atmosphere and climate. Okay, so that's it for global atmospheric circulation. You may be asked how it's like influences tropical storms and circulation would be asked to describe this whole process. But yeah, I hope you understand it. If you have any more questions, feel free to put it in the chat again. And yeah, so I'll just move on to another topic. Let me find another one. Okay, so after I've covered that, now we're going to look at the last bit of topic 1A, which is going to be climate change. So you can see I've skipped over the examples and case studies because next week I'm doing a whole live stream where we go through all of the examples and case studies. So today we're just focusing on the content and the non-case study content. So let's do some climate change revision. Okay. So, what is climate change? Firstly, you may be asked to define what climate change is. So you need to know that climate change is any significant change in Earth's climate over a long period. So any significant change in the Earth's climate over a long period of time. Okay, so key things here that you need to know: any significant change, and also a long period of time. So we have different periods of time, and the climate, because climate is always changing, the weather changes every day. So what we mean by significant is something that has a massive impact on the climate change and can be recorded and shown consecutively. So there's different periods which you need to know about of climate change. There's the Quaternary period. Now, the Quaternary period, this is the most recent geological period. And this happened 2.6 million years ago. So you could just tell how long the periods are. So if the closest one we had to us was 2.6 million years ago, that means that so far we're 2.6 million years into the current period. Now, in the period before the Quaternary, the Earth's climate was actually very warm and very stable. So if we're looking at what happened before, the Earth's climate was warm and very stable. So we had this period before Quaternary period, which is warm and stable. Then we had the Quaternary period, which is the most recent geological period. And then during the Quaternary period, you're going to need to know some key facts here. So firstly, global temperature had shifted between cold glacial periods that lasted for 100,000 years and then warm interglacial periods that lasted for 10,000 years. So the Quaternary period was practically a cycle. It was a cycle between two different things. The first was the cold glacial periods. And then the second was the warm interglacial periods. Now we know, as we said, that this Quaternary period was very stable, which just means that the cold interglacial periods would always be roughly 100,000 years, and then the warm interglacial periods will always be 10,000 years. Now, the last glacial years ago, since the climate change has been warming. So what it's saying is global warming has caused a tiny effect in this Quaternary period, and that is the reason why people think that global warming is an issue. So, global warming is the term used to describe the sharp rise in temperature over the last century. So global warming is actually a type of climate change. Remember, we said climate change is any significant change in the Earth's climate for a long period of time. And we note that a type of climate change is global warming because we've seen a sharp rise in temperature over the last century. Now, there's key evidence for climate change, which suggests that climate change actually exists. So let's look at some of the evidence. What's the proof? Well, evidence for climate change, things like ice sediment cores, sediment cores. Then we also have other things such as tree rings. We have pollen analysis, but pollen analysis isn't necessarily that useful. That's why it doesn't often come up. But let's talk about it. Pollen analysis. And then temperature records, which again isn't that useful because we only started recording temperature or being able to record temperature within the last century. So just discussion about each one. So ice and sediment cores. So what this does is using our information about the fact that ice sheets are made of layers of ice. So there are layers, and within each layer, it's formed every year. So the layers of ice are formed on a yearly basis. And therefore, this is saying that because it's being formed each year, if you drill deep enough, scientists can get really long cores of ice, and by analysing the gases trapped in those layers of ice, they can then tell what that temperature was that year. So the layers of ice formed on a yearly basis, this then allows scientists to drill for really long ice sediment cores, which will tell you something about the temperature that year. Now, pollen, the next one, gets preserved within sediment or peat bogs. And because it gets preserved, and pollen indicates the species in which they grow in and which they come in. So the scientists can then identify from the pollen what species were living at that time, and they also know the conditions in which they lived in. And finally, temperature records. So temperature records, they only date back to the 1850s. However, they can still tell us something useful about the records of temperature change. And unlike ice cores, tree rings, and pollen analysis, this is actually the most reliable, but it's short term. But it is the most reliable because it's scientists' accurate measurements. Now, we also need to know some causes of climate change in both natural factors and human activity. So let's look at it. Causes of climate change. So there are natural factors which cause climate change, and then there's also human factors which we have caused and are genuinely quite negative in comparison to the natural factors. So the natural factors, firstly, we have orbital changes. Now this is referring to how much solar radiation we receive is different. So the amount of solar radiation is different. It changes, it's volatile. So solar radiation is one factor. And then also there's variations in the way in which the Earth orbits the Sun. So the Earth orbits the Sun in various different ways. Now, I've never seen a question on this, but it's always good to know because it is in the specification. So, different ways in which the Earth orbits the Sun. So, there's one thing called the stretch. So, you can imagine this is when it doesn't. The Earth should orbit the Sun in a circular way, but the stretch is when the Earth's orbit looks more like an oval. Then we have the tilt. The tilt is literally the Earth's axis. And the change in the Earth's axis, or the tilt, can actually change how much solar radiation we receive. And finally, the wobble. So the wobble is the fact that the Earth wobbles as it moves around. It doesn't just move around at a perfect rate, it moves and wobbles. So as it moves like a spinning top, this can also create changes into the amount of energy that the Earth receives. So because of the stretch, which is the Earth's oval orbit, the tilt, which is the axis of the Earth, and the wobble, which is how the Earth moves, we then receive variations in the amount of solar radiation we receive, and therefore we receive variation in our climate. So that's one factor. Another factor is volcanic activity. Now, don't be fooled into thinking that the more volcanic activity, the hotter it will be, because it's actually the other way. When we have volcanic activity, volcanoes can sometimes eject large quantities of materials. And these materials, some of them are ash and pyroclastic flow. Now, ash is really bad because it contains things like carbon monoxide, and it also blocks out the sun. So because the ash is in the atmosphere, what happens is, instead of having the Earth normally receive its amount of radiation, the volcano ejects this ash onto a certain part, and then it reduces the amount of solar radiation received, because it not only blocks out the sunlight, but it actually reflects the sunlight. So it reflects the sun's light back out into space. So the more volcanoes and volcanoes exist, and therefore the more solar radiation the Earth is deflecting. Now we also have the third and final natural factor, which is called solar output. And obviously this just means how the sun's energy output isn't always the same and isn't always consistent. It changes and varies. So there's actually cycles to prove that there's the sun's energy pattern is every 11 years, but that's not necessarily what you need to know. But just so you know, it changes roughly every 11 years, which means that the climate change changes every 11 years. Now that's the natural factors. So orbital, volcanic, and solar output. Let's look at the human factors. Now, I'm pretty sure you'll be well versed with this in many of the subjects we talk about human factors. So things such as burning fossil fuels, things such as increased farming, especially cattle farming, because that releases a lot of methane and takes up land as well. Deforestation, by increasing the carbon dioxide output, you're then increasing the amount of energy absorbed by solar radiation. And weirdly enough, another thing is cement production. This is probably one you did not think of. So cement production is made from limestone, and limestone has a lot of carbon in it. And because of that, when cement is produced, lots of carbon dioxide is released into the atmosphere. So cement production has something called limestone. Limestone contains carbon, and carbon then creates carbon dioxide. Okay, natural factors. The final bit of climate change is what are the effects on the environment and how can we stop the effects? Okay, effects of climate change. So, in terms of the effects of climate change, firstly, temperatures are expected to rise from 0.3 to 4.8 degrees Celsius. So it can rise all the way up to 4.8 degrees Celsius by 2100. Actually, a massive increase in comparison to what we've had before. Now, this then causes major effects. So because of this temperature increase, it has major effects and major cycles. So if we increase the temperature, this means that there's more likely for glaciers and ice to start melting. Now, when this melts, this means that water stored on the land is returning to the oceans, and this then causes the sea levels to rise. So increase sea levels to rise, and also an increase in the amount of animals that are going to become extinct because many of them live on these glaciers and ice sheets. And when the sea levels rise, this means that low-lying areas, so like floodplains and flat continents and countries, are at a higher risk. So example, Miami is very low lying, so if sea levels were to rise by a significant amount, Miami would be a place where it will be in a lot of danger. Now this then means also, if there's increased sea level rise, this means that there's also increased coastal. If your school studies, you will know that if there's increased coastal erosion, this then means that more coastal areas will be submerged. More coastal areas will be submerged, and therefore more people will become homeless and have to move, and then the population density will have to increase as people move to cities. Now, precipitation patterns will change as well. Also, migration patterns for things like birds who rely on certain temperatures in order to move. They'll get confused, and therefore a lot of their species can actually go extinct if the migration pattern is messed with. And finally, the distribution of different species. So some species are having to move to higher and higher latitudes because it's getting too hot where they're currently living. Now this then changes predator-prey cycles. Okay, so there are loads of effects of climate change in terms of effects on humans as well, because that's just effects on like the world and animals. In terms of humans, it will increase the amount of deaths caused by flooding. It will increase the number of tropical storms as well, which will further increase the number of deaths, injuries, the number of people going homeless. And especially with the fact that the population is only increasing, yet the resources and facilities are decreasing, this then means that people are going to struggle more. So food security is actually going to decrease, and there will be outcry, public bursts, especially in the poorer countries, which are constantly being affected by these natural hazards, the climate change will only cause it to increase. Okay, now enough with the negatives of the effects of climate change. Let's talk about some strategies to overcome it. So the first one is mitigation. And the second one is adaptation. So I'm pretty sure you know what adaptation means. Adaptation means adapting. So adaptation strategies will be, how do we adapt to, or did you ask, is there a greater chance of tropical storms? Yes, there is. So what happens is, because there's increased temperature rise, this means that in order for tropical storms to form, they require certain temperatures, and they require a sea temperature of 37 degrees Celsius or something like that. I think 37 or 27 degrees Celsius. And if there is an increased sea temperature, then that means that tropical storms are more likely to form in areas which they haven't been formed before. So yeah, that is correct. Um, but yeah, and adaptation strategy. So adaptation is responding to the effects of climate change, whereas mitigation is trying to reduce the causes of climate change and trying to stop climate change, which seems to be what we're doing right now. So let's see some examples of mitigation. Firstly, carbon capture. So this is when it's designed to reduce emissions by capturing carbon dioxide and then transporting it to safer places where it can be stored, so underground or something like that. So it's taking the carbon dioxide from the atmosphere and putting it underground. Another strategy of mitigation is planting trees, also known as afforestation. Another mitigation strategy is alternative energy. So a switch to using more renewable energy that is derived from fossil fuels, which are going to run out one day. So in the UK is actually, fun fact, the world's windiest place. So we could definitely take advantage of that by using things like wind farms. Okay, and the final mitigation strategy is international agreements. So this is things like the Paris Agreement, which reduces greenhouse gases and limits global warming, and how each country within the EU and within the UK have submitted a pledge to say how they will try to stop greenhouse gases from being emitted and things like that. So that's mitigation. Now let's talk about some adaptation. So this is things that are enabling us to just live with climate change and how we can deal with it as opposed to trying to stop it from happening. So some things are changing agricultural systems. So this is changing the way we farm, and more specifically what we farm, because of the fact that there will be changing rainfall patterns and changing temperatures. This will then affect the productivity of existing systems. Now some people in England might think that it's a benefit, that because the temperature is increasing, that means that we can grow quite a lot more of our foods within England and therefore have to stop importing it from other countries. Now, in some regions, things like biotechnology are being used to create new crop varieties that are more resistant to extreme weather events. So, we're using science to create crops that can be stronger and therefore not be destroyed by extreme weather events. For example, drought resistant rice. Okay, now another method of adaptation is managing the water supply. Now, what I mean by this is that dry areas are only predicted to get drier, which is a real problem. And this means that there will be water shortages even more in those countries. So, where will people get their water from? We're suggesting that if people in higher income countries, if we were to use our water more efficiently, then we could then help those other countries. So, things that we could do is use water meters. Now, water meters are supposed to discourage excessive water use by telling you how much water you've used. Things also like recycling rainwater and recycling wastewater to be collected and recycled. Now, the final method of adaptation is coping with rising sea levels. Now, what does this mean? At the current rates, sea levels are predicted to rise about 65 centimetres by 2100. Now, what this means is that many islands and many coastal areas would therefore flood. So, we need to stop this. How can we stop this? By increasing the flood warning systems that are being put in place, increasing the physical defences, so things like flood barrier. In London, actually, the Thames barrier was put into place so that it could be closed to prevent any seawater flooding around the city. In areas that can't afford these expensive flood defences, however, they build other things. Like in Bangladesh, people are building raised flood shelters and build houses. So people are doing the can to prepare themselves for these extreme weather events. Okay, so that is now a lot of this topic done. We've covered the major topics in 1A. One thing we didn't cover was how tropical storms form. So I'm going to quickly cover that now, and then we can do some exam questions and then finish at 8:40-ish. Okay. So let's look at how storms form. Okay. So there are certain things that tropical storms need to form. So firstly, they must develop between 5 degrees north and 30 degrees south of the equator. So we looked at, when we were looking at, where is it? The global atmospheric circulation model. We now know that tropical storms can only develop between 30 degrees north of the equator and 5 degrees, so 30 degrees and 5 degrees north and south. So in this area here and in this area here. So not right by the equator, but just above and below the equator. So first thing, it needs to be between 5 degrees north and south and 30 degrees north and south of the equator. The second thing is it needs to have a certain temperature. So sea temperatures need to be at least 27 degrees. So not 37 degrees, 27 degrees. And wind shear also needs to be relatively low. So wind shear is just the difference in wind. So it's the difference in wind speed. So is it high low speed? Is it low speed? So what we basically need to say is that there needs to be low winds. That's what we mean by wind shear. Now, let's talk about how the tropical storms form. So what happens is the warm surface water rises because, as we know, anything warm always rises. And as it rises, it then begins to condense into clouds. So let's draw these clouds. Okay, so now as it begins to condense into these clouds, what happens is this then releases lots and lots of energy. Now, as this releases lots and lots of energy, this then begins to create a powerful storm. What happens is the rising air creates an area of low pressure, because as we know, rising air creates areas of low pressure. And then this increases the winds at the top. So low pressure at the bottom, winds at the top. Now, as there are winds at the top, this then means that the clouds and the precipitation that are being condensed then begin to spin. The storm to spin. Now, as it causes the storm to spin, this then means that there's a center of the storm. So within the center of the storm, there's low pressure, because this is the continued warm air rising. So in the storm, as warm air rises, there's low pressure. And then outside of the storm, there's the clouds with very, very high pressure because of the winds. High pressure winds. Now we call the center the eye. So the eye of the storm. Now the eye is actually surrounded by something called the eye wall. The eye wall is the spiraling rising air and there's very strong winds around this, but within it it's quite low pressure, and there's also some precipitation in the eye. Now, as we said, we have this massive eye wall here, and the eye wall is like this and this bit, and then this eye wall is the very high pressure winds circling the storm. Now, towards the edges of the storm, the wind speed begins to fall. So the wind speed is highest here and lowest here. So here the wind speed is very low. But eventually, as the storm grows and it's powered by the heat of the water, it's powered by this warm surface water. So as it then grows and grows, then the storm becomes larger, the eye becomes larger, and the eye wall then widens as well. Now, overall, this tends to be roughly 300 kilometers in length, which is very, very large. That's the average storm. So that is how the storm forms. But let's talk about how the storm moves, because the storm is not normally where it forms is not the issue, but where it moves and where it affects is the issue. So let me get an image of tropical storms formation, because that will be easier. So I'm pretty sure you've seen this map that I'm going to show you soon. So let me... Okay. So this is the tropical cyclone distribution. Now what we have here are where the tropical storms tend to lie and where they affect. So most tropical storms are caused by between 30 degrees north of the equator and 30 degrees south of the equator. So around the yellow lines. So that's where they're made. But if they're affecting areas like here and areas here, then that means that they must move. Now, you may know all these different names for them: typhoons, hurricanes, cyclones, but in reality, they're all the same thing. Now, if a tropical storm, was to form here, and then the winds could move it over here, then it'll be known as a cyclone. If it was to form here and move to the Americas, then it will be known as a hurricane. So it's not where it's formed, but it's where the tropical storm affects it, is where it gets its name. And you need to know roughly the areas in which cyclones and typhoons form. You may be given this map in the exam. Now, easterly winds near the equator move tropical storms towards the west. So if it's near the equator, then the tropical cyclones or the tropical storms tend to move. The storms then spin how the Coriolis effect, which we discussed earlier. And the Coriolis effect is how the air moves due to the curvature of the Earth and due to the fact that the Earth is rotating. So it doesn't move. So as tropical storms attempt to move westward, it then also moves at this angle, which is how it can go all the way as high as to affect the hurricanes or the cyclones. Now, as a storm moves over the ocean, the energy from the warm water strengthens the storm. Now, as it strengthens the storm, this means that there's more energy. Therefore, the wind speed increases. But when do the storms lose energy? Because eventually the storms will have to lose energy. Well, storms lose energy the moment they hit landfall. So imagine there was a storm here, and it was moving across and across. And once it makes landfall, what happens is it then begins to lose all of its energy. And the reason why is because it was gaining the energy from the warm sea water. However, when it hits landfall, this energy is no longer there because it's above the land, it's above the sea, and therefore it loses energy. Which is why the storm, when it hits at an area, it then eventually dissipates. It doesn't just go right through it. Now, the majority of the storms occur within the northern hemisphere. So the northern hemisphere is from here. So the majority of the storms that occur within the northern hemisphere occur from August to October because of seasons and how seasons vary. And the majority that occur in the southern hemisphere occur from August to October. Not August to October, December to April. So we can see, however, that most do not actually occur in the southern hemisphere because we know that the Coriolis effect tends to move them in this direction. However, because of climate change and the fact that sea level temperatures are only rising, this then means that more tropical storms are going to be affected, and this an increase as we see them affecting more and more areas. However, the UK is not in danger because of the weather systems there. Okay, so now we've practically gone through all of the content for 1A, challenges of natural hazards. I'm now going to get some exam questions which we can look at and do some practices with. So just bear with me for 1 minute. Okay, so I was unable to get the document with the exam questions on it up, so I'm just going to show you on here and type them as we're going across. So the first question is a one marker, and it's just define a natural hazard. So this is a one marker, and things you're expected to write just for this one marker. Um, you can pause this and have a go, by the way, as we're going through it. But firstly, you need to say that natural hazards are one, a natural event, and the second thing that you need to say is that it can cause um an it's things such as earthquakes, volcanoes, and tropical storms that threaten people or have the potential to cause damage, destruction, and death. So a natural event that has the potential to cause damage, destruction, and death. So if you see that question in the exam, you know exactly what to write. Okay. The next question. Suggest how a hazard risk would be affected by an increase in population. So, suggest how a hazard risk would be affected by an increase in population. By an increase in population. So what this is saying here is, remember, hazard risk, as we talked about in the beginning of the live stream, is the hazard risk is the chance that you'll be affected. The chance you will be affected by a hazard. Now, what this is saying here is, how is the chance you'll be affected by hazard increased when there's an increase in population? Well, first of all, you have to say this. Then you have to say, as there's an increase in population, that means that there's an increase in chance that people will be affected because there's more people to be affected. So what you could say is, hazard risk is likely to increase when there's an increase in population because there is a potential for more people to be vulnerable, and therefore the likelihood of death increases. An increase in population could mean more housing and therefore potential for damage, and an increase in population near hazard-prone zones due to cost or availability could also increase. Okay, now since we don't have much time, we have 1 minute left, I want to give you one question for you to do and hopefully revise from. And this question is, describe the global distribution of earthquakes and volcanoes in relation to plate margins. This is a 3 marker, and this is the question I want to leave you with. You feel free to put your answers in the comments below. And this is what I'll leave you with today. Now, I just wanted to say thank you for everyone who turned up. It means a lot. And also, I hope you do really well in your GCSEs, because I definitely know that you're working hard, especially if you're up this early doing some work. I've left the question up on the board if you want to do any more practice with it. And again, yeah, thank you for watching, and happy revision and good luck with your revision.